Welcome to Plutus IAS. So today we are going to see some standard examples of group and subgroup. So we'll see that GL, that is called the general linear group, and are defined as Mn such that determinant is not equal to 0. We'll prove that this is a group and also so that define SL, special linear group, same NR that A belongs to Mn such that determinant A equal to 1, that is a particular. Obviously this is a subset of GL, general linear group, and the SL is called the special linear group. A belongs to Mn, that means square matrices of order n whose determinant is equal to 1. So we will prove that first that this is a group, and second we will show that this SL is subgroup of GL. So first we will see that here this is a group or not. So first we will see that the closure law hold or not. So now let for closure law it belongs to, let AB belongs to GL. That implies that determinant A not equal to 0 and determinant of B not equal to 0. If AB belongs to G, then closure law holds. So we will find the determinant of A dot B. So now we shall find the determinant of A dot B, and we know that the determinant of A dot B equal to determinant of A dot determinant of B, and that is not equal to 0. Since determinant of A not equal to 0 and determinant of B not equal to 0, therefore determinant of AB also not equal to 0, and that implies that A dot B belongs to G for all AB belongs to G. In short, we are taking the GL as the G, so we can write here. Here we can also write the G at the GL for all AB belongs to GL. That means closure law hold. Now we'll see what about the associative law. So matrix multiplication satisfy associative law. That is the reason matrix multiplication satisfy. Matrix multiplication satisfy the associative law. And what about the existence of identity? Existence of identity. So we know that the determinant of identity matrix of n plus n is 1, since I and determinant of this equal to 1. Therefore, I n belongs to GL such that A dot IN equal to IN dot A for all A belongs to GL. That means imply that identity matrix here, identity matrix IN is the identity element of general linear group. And next we will check whether the inverse of every element exists or not. So existence of inverse. So let's take any element. Let A belongs to GL, and that implies that determinant of A not equal to 0, and determinant non-zero, that means matrix is non-singular, and non-singular matrices has the inverse matrices. So imply that A inverse exists and determinant of A inverse is also not equal to 0. Thus for each A belongs to GL, we have we have A inverse belongs to GL such that A dot A inverse equal to identity matrix equal to this. That means every element implied that every element of GL has inverse element in GL, and hence GL and here R means entries of matrices are real number and N means N square matrices. Here is a group. Group with respect to matrix multiplication by the operation. And obviously that is not commutative, as matrix multiplication doesn't satisfy the commutative law. So this is a non-abelian group. Now second, we have to show that SL is a subgroup. So clearly SL and R is subset of GL and R. To show the subgroup, we know that what we have to do actually. First, show that for any subset of G, if G is a group, first we have to show that H is non-empty, and then show that if A operation B inverse belongs to H, for all AB belongs to H, then H is subgroup. So here first we will see that this is a non-empty or not. So we know that since determinant of IN equal to what? 1. That means identity matrix of N square, determinant of IN equal to 1. That implies that at least one element obviously belongs to SL, and that implies that SL and R is non-empty. So first H is non-empty. Second, we have to show that AB, for each AB belongs to H, AB inverse also belongs to S. So let AB belongs to SL and R, and that implies that what? Determinant of A equal to 1 and determinant of B equal to also 1. Okay, and the property of SL is what? Determinant of matrices is equal to 1. Only those matrices are belongs to SL. So determinant A not equal to 0, determinant B not equal to 0, as determinant is equal to 1. So obviously that also implies that B inverse exists. So now we will find B inverse exists, and now determinant this equal to 1. So B inverse will be also. So now first find. So let therefore determinant of AB inverse equal to determinant of A. Yes, sir. We have to find what? We have to find AB A inverse GH inverse. So just let any element the G AB inverse. Okay. Now AB inverse belongs to S, for all AB belongs to S. So now find the determinant of AB inverse equal to what? Determinant of A and determinant of A inverse equal to 1 into 1 equal to 1. That means imply that AB inverse belongs to SL and R for all AB belongs to SL and R, and hence SL is a subgroup of GL. That means special linear group is a subgroup of general linear group. So that's it. So we will talk more about this group. That we will also prove that this is a. Now you can also show that the SL is a normal subgroup of GL. So we will see more examples about the group theory in upcoming videos. Thank you.